Hi, now we are discussing on homomorphic unit as in the part of asymmetric synthesis in stereochemistry. Now, what is homomorphic unit? Okay, in that, what is unit? Okay, so here unit may be ligand or phase. Okay, here ligands may be atom or group, and phase, that is sp2 carbon or sp2 hybridized carbon. Okay, in homomorphic unit, the word unit indicates ligand or phase. Here ligand may be atom or group. Okay, and phase indicates sp2 hybridized carbon. Okay, right. And how can we define homomorphic unit? Okay, just first check the example here, and if you observe this example, it has two carboxylic acid groups on vertical line and two hydrogens on horizontal line. Okay, right. And if we observe the two hydrogens on vertical line, we are calling them as homomorphic because the two hydrogens, okay, the two hydrogens having same physical and chemical properties. Okay, the two hydrogens having same physical and chemical properties. Hence, we are considering them as homomorphic on this molecule. Okay, right. And if you observe the same molecule and if you consider carboxylic acid group and hydrogen, they are not homomorphic because carboxylic acid group and hydrogen have different physical and chemical properties. Okay, right. And if you observe the same molecule with two carboxylic acid groups, they are called as homomorphic. Okay, because they have same physical and chemical properties. Right? And how can you define homomorphic unit from this? Now, here the atoms or groups, okay, like here ligand or phase, if we consider, if the two ligands on the molecule, okay, by applying symmetrical elements or symmetry operations through the molecule and or by the substitution or by the hypothetical substitution of the reference groups, okay, if they produce stereoisomers, okay, with homo, enantio or diastereo relationship, then those groups or atoms, here ligand or phases on the molecule, considered as homomorphic unit. Okay, so now in our simple words, how can we define homomorphic unit here? So if we consider these two hydrogens are reference hydrogens, okay, reference units, and by applying symmetrical operations on the molecule, okay, like plane of symmetry or center, that means inversion of symmetry or proper axis of symmetry or improper axis of symmetry. Okay, any of the symmetrical operations are possible on the molecule, okay, through the reference hydrogens. Here we are considering the units or hydrogens. Okay, so by the symmetrical operations or by the substitution, that means if we substitute in the place of hydrogens with other third different group or atom, okay, if by doing all these operations or symmetrical operations or by the substitutions, if they produce stereoisomers with the homo relationship or enantio relationship or diastereo relationship, then these two hydrogens are considered as homomorphic units. Okay, understand? Here these two hydrogens are considered as homomorphic units whenever they produce homo or enantio or diastereo relationship containing products, whenever symmetrical operations are operated on the molecule or by the substitution of the reference hydrogens. Okay, right. Now check this molecule if you observe this molecule, hydrogen and hydroxy groups are not homomorphic because they doesn't have any similar physical and chemical properties. Okay, and they doesn't produce stereoisomers with homo relationship or enantiomer relationship or diastereo relationship. Okay, and at the same time, if we consider chlorine and phenyl, these are two different, hence these two ligands or these two groups or these two atomine group are not considered as homomorphic units. Okay, but here phenyl or chlorine are considered as homomorphic units because by the substitution of one chlorine we can get one stereoisomers, by substitution of other chlorine we can get other stereoisomers. So there is the possibility of different homo relationship or enantiomer relationship or diastereo relationship in the products of stereoisomers. Then we consider these two chlorine units as homomorphic. Okay, right. Now check what is phase here. Okay, homomorphic phase. What is homomorphic phase? Till now we are just discussed on homomorphic unit, that means homomorphic ligand or atom. Now we are considering homomorphic phase. Okay, just check this example, that is ketone here, and on this ketone, that means sp2 hybridized carbon. Okay, so consider this is a plane. On the plane we have carbon, oxygen and two alkyl groups on the plane. Okay, so from the above the plane we consider that as top phase. Okay, by the if we add any nucleophile onto the carbon from the top phase, that means on the plane. Okay, so then we consider that as top phase, and if the addition takes place from the bottom of the plane of the carbon, that means that keto molecule. Okay, then we consider it as bottom phase. Okay, right. Now just check the sentences here. If upper and lower phases are not distinguishable, then the phases are said to be homomorphic phases. Okay, right. And here just consider the groups or the ligands on the sp2 carbon. If they are similar, if they are same, then the top phase and the bottom phase are not distinguished. Okay, hence they are called, the phases are called as homomorphic phases. Right, and if upper phase and lower phases are distinguishable, then those phases are not considered as homomorphic phases. Okay, so we can observe that if R is not equal to another R on the sp2 carbon, then the phases, top phase and bottom phase, are not homomorphic. Okay, right. And check duster here. So that is a simple and common example we can give to understand, to give the best analysis to understand the phases. So consider the duster. On duster, the top phase which contain cotton, so that is different phase with plane on it. Okay, so consider that is a top phase, and the bottom phase, that means the wooden part of the duster, is considered as another part, that means a bottom phase. These two phases are different, right? On the top phase we have cotton planarity, and in the bottom phase we have wooden plane. Okay, so these two phases are different, hence the duster phases are not homomorphic. Okay, right. Now to check homomorphic relationship, we must detach reference atom. So here we are considering hydrogen atoms as reference atoms to know the relationship of the stereoisomers in the products. They may be homo or enantio or diastereo topic. Okay, right. Now in a molecule, selected reference groups under detached condition or in isolation, constitutionally, configurationally identical reference units are called as homomorphic units. Okay, right. Now homomorphic units are two types, and they are homomorphic ligands and homomorphic phases. Okay, for just here consider homomorphic ligand. For this example, and we have labeled the 4 hydrogens, okay, 1 2 3 4, to physically differentiate them. Okay, so they are equal chemically, but physically to differentiate, just we are labeled the hydrogen. Okay, and as we said, by applying symmetrical element or symmetrical operations on the 4 hydrogens, or by just substitution, okay, with another different group on H1, H2, H3, H4, okay, we get the different stereoisomeric relationships, like that may be homo relationship, or enantiomer relationship, or that may be diastereo relationship. Okay, so then we consider these 4 hydrogens are homomorphic ligands. Okay, right. And check another example for homomorphic ligand here. If you consider this molecule, in this, the center one, okay, so on the above or the top of it, we have one group, and then the bottom we have the group. These 2 groups are same. Okay, these 2 groups are constitutionally and configurationally and structurally same. Hence, these 2 groups are considered as homomers. Okay, right. I now check homomorphic phase here. Carbonyl molecule on the top phase. So this is top phase and this is bottom phase. As we said, on the carbonyl molecule, if the ligands are same, here if R equals to R, then the relationship of the phases on this molecule are homotopic phases. Okay, right. Now check homotopic unit. Okay, as in the part of homomorphic units, now we are discussing homotopic unit. Okay, homotopic units are again classified into 2 categories: homotopic ligand and homotopic phase. Now consider homotopic ligand. If the selected homomorphic ligands in a molecule are interchangeable with CN, that is proper axis of symmetry element, then the ligands are called as or considered as homotopic ligands. Okay, so what is the important point in this, the definition of homotopic ligand? That is, if we observe the selected homomorphic ligands with CN symmetry element relationship. Okay, that is, if improper axis of symmetry is possible through the selected homomorphic ligands in a molecule, then those homomorphic ligands are considered as homotopic ligands. Okay, and on hypothetical substitution of homomorphic ligands with third different group or ligand, if produces identical products, then homomorphic ligands are considered as homotopic ligands. Okay, so what we said, on hypothetical substitution of homomorphic ligands with third different group or ligand, if that operation produces identical product, then those homomorphic ligands are considered as homotopic ligands. Okay, right, consider this example here, and on vertical line we have X and X. So to physically differentiate, we have labeled them as X1 and X2, and on horizontal line we have H1 and H2. Okay, right. So here is the possibility of 2 C2s. Okay, 2 principal axes are possible on the given molecule. Okay, if we consider the C2 axis through 2xx, that means on vertical line, by rotating it, we get H2 takes position of H1 and H1 take position of H2. Okay, so if we remove the labels on the hydrogens, we get the same molecule as the parent one or the substrate. Okay, so they are here, by the C2 rotation, we are getting 2 similar, that means the substrate and the product are same. Okay, these 2 are same. Hence, these homomorphic ligands, that is H1 and H2, are considered as homotopic ligands. Okay, so what is the definition of homotopic ligands here? Simply, if CN is possible through the 2, that means the ligands, okay, which we are considering. Okay, here homomorphic ligands, then those ligands are called as homotopic phases, homatopic ligands. Right, now check if plane, that means C2 axis is passing through the H1 and H2, then we can get this one as a stereoisomers. That means x1 takes its x2 place and x2 takes x1 place. Okay, by removing labels on x1 and x2, we get the same molecule as the substrate. Okay, hence we can say x1 and x2, that means x1 and x2 are homotopic. Okay, right. Now check another example, that is alkene. We have labeled 1, 2, 3, 4 and hydrogen to distinguish physically. Okay, and we need to check the C2 axis or CN, proper axis symmetry, is there possible in the molecule or not. If it is possible, then there is a possibility of homomorphic the relationship. Okay, homomorphic relationship, right? And homotopic relationship, we can say, and if the C2 is passing through the carbon and carbon, then H1 gets H2 position and H2 gets H1 position. Hence we can say H1 and H2 are homomers and H1 and H2 ligands are homotopic ligands. Okay, or homotopic hydrogen. At the same time we can say H3 and H4 are homomers and homotopic, they are in homotopic relationship. Okay, and if the C2 is passing through the in between the two carbon double bond, okay, then H1 gets H4 position and H4 gets H1. Like that, H2 and H3 are homotopic relationship, and H1 and H4 are in homotopic relationship. Okay, and just check another example here. That means chloromethane. There is a possibility of principal axis CN through the chlorine and carbon. Okay, by each rotation of 120 degrees we get equal, that means same arrangement. Okay, right, that means we get a same hydrogen. But here we have labeled H1, H2, H3. If we remove 1, 2, 3 labels on each 120 degrees, we get the same molecule. Okay, hence we can say H1, H2, H3 are homotopic. Okay, and now check another example here. There is a possibility of C2 through this molecule from that one, okay, methylene bridge, and through the molecule, and here by 180 degree rotation H1 gets H2 position and H2 gets H1 position. Hence H1 and H2 are homotopic in relationship. At the same time, just check all of them, these are all having C2 symmetry operation through them, hence they are homotopic. Just consider here H12, which is labeled 12 for that hydrogen, and H6, here is the H6. So on C2 rotation, then H6 takes H12 position and H12 takes H6 position exactly. Okay, hence H12 and H6 are homotopic in relationship. Okay, right. Now substitution criteria. Okay, till now we have discussed it based on symmetry operations. Now check substitution criteria. That means the reference hydrogens, what we are calling them as homomorphic hydrogens, if those are replaced with other third different group, then how they can produce a homo or homo or enantio or diastereo relationship in the product stereoisomers. Okay, right. Now here, if H1 on this molecule is replaced with bromine, we get this stereoisomer, and H2 is replaced with bromine, then we get this stereoisomer. Okay, these two stereoisomers are same. Okay, because just 180 degrees rotation of this molecule, bromine takes H position and H takes, that means hydrogen takes bromine position. Okay, by that we can get same molecule as this one. Okay, so here these two are homomers. Hence H1 and H2 on this molecule are in homotopic relationship and they are homotopic hydrogens. Okay, right. And check another example here. In this example, if H1 is replaced with chlorine and H2 is replaced with chlorine, we get these two stereoisomers. Okay, and on 180 degrees rotation. For example, if you rotate this molecule, so here from like this, okay, through this 180 degrees rotation angle, okay, or on axis, we get chlorine here, right? And then further by taking principal axis, that is C2 axis, on horizontal line, we get the same molecule as like this. Okay, just try to check that. And here by that we can say there is a possibility of CN, proper axis symmetry, through the stereoisomers which are produced from this molecule by replacing H1 and H2. Hence, these H1 and H2 are simply considered as homotopic in relationship. They are homotopic ligands or homotopic hydrogens. Okay, right. Now check another example, that is allene. On allene we have labeled hydrogens on 1, 2, 3, 4 like that. And if H1 is replaced with Cl, we get this one, and H2 with Cl we get this stereoisomer, and H3 and H4 we get all these different stereoisomers here. Okay, I now consider on H1 H2 relationship. By substitutions with chlorine, we get these two stereoisomers, and they are similar, they are same. By just taking a C2 axis, or by just rotating one stereoisomer, we can get another stereoisomer. Hence, H1 and H2 are in homotopic relationship, and these two stereoisomers are homomers. Okay, right. And check H3 and H4 here, and by passing that means by passing Cn, that means a C2 axis of symmetry through the stereoisomer, we can get another stereoisomer. Okay, so by that we can say H3 and H4 on the given molecule are in homotopic relationship. They are homotopic hydrogens. Okay, right. Now check homotopic phases. If two phases of a molecule interchangeable with proper axis of symmetry element, then phases are homotopic. Okay, what are homotopic phases? If two phases of a molecule interchangeable with principal axis of symmetry element, then the phases are called as homotopic phases. Okay, at the same time, on hypothetical addition of two different phases, that means from top side and from bottom side or bottom phase of a molecule, if produces same products, then the phases are considered as homotopic phases. Okay, just consider here one of the example to explain homotopic phases. Here consider one keto molecule, and the dotted lines indicates this is a plane on which we have carbon and two hydrogens and one oxygen. Okay, just imagine, and this is top phase. That means we are adding nucleophile from the above, that means from the screen onto the plane. Just imagine like that. And this is the bottom phase of the carbonyl molecule which is on the plane. Okay, that means we are adding from the bottom side of the screen onto the carbonyl group. Just imagine like that. Okay, right. And if we do that, we have two hydrogens on the sp2 carbon. They are same. Hence, there is a possibility of C2. Okay, proper axis symmetry, that is C2 is possible, then we are considered as these two phases, top phase and bottom phase, or homotopic phases. Okay, and just consider another example here, and on sp2 carbon, if the two similar groups are there, then there is a possibility of two phases, that is top phase and bottom phase, or in homotopic relationship. Okay, that can be explained in all these examples. Right, now just take another, that is addition criteria. If we check addition criteria, in these examples we have taken based on symmetry operations. Okay, by just taking symmetry operations, we can produce homotopic relationship in the top phase attack or bottom phase attack. Okay, due to the possibility of symmetry operations, right? And hence we are called them as homotopic phases. Now consider addition criteria. Right, now just take the same molecule, that is carbonyl molecule, and from top phase of the planarity of the carbonyl group, then that is by reacting with hydrogen cyanide, the nucleophile cyanide attacking from the top phase. Just imagine like that. And if that happen, the oxygen goes back side of the plane, and the CN which is added from the top phase gets above on the plane. Okay, it takes a place above the plane of the molecule. Okay, right. And if cyanide nucleophile attack on the carbonyl carbon from the below of the planarity of the given molecule, okay, then OH gets its that means it is projected towards us. Okay, it is above the plane, and at the bottom side we have CN. Okay, right. And these two are similar. Okay, and these two isomers here, stereoisomers, are simply homomers, because just check the produced stereoisomers. Is there the possibility of proper axis symmetry on them? Okay, just by applying C2 rotation, we get this one. Okay, if C2 is proper axis symmetry, or C2 is majorly possible through the one stereoisomer, and if it produces another stereoisomer, then we can say that those two stereoisomers are in homotopic relationship. Okay, and those are homomers. Okay, now we can say the two, that means top phase and bottom phase, are in homotopic relationship, and those phases are homotopic phases. Okay, right. Now check another example. In this example, and if top phase attack of cyanide nucleophile and bottom phase attack of nucleophile, we get these two stereoisomers, and on these two stereoisomers there is a possibility of CN, that is C2 axis. By rotation we can get one stereoisomer to another stereoisomer. Hence we can consider them, these two stereoisomers, as homomers. Okay, right. And the phases on the substrate are considered as homotopic phases. Okay, because already we said that on the sp2 carbon, if similar groups are present, then the product, that means the resultant stereoisomers, simply become homomers. Okay, and the phases or the ligands on the substrate are in homotopic relationship. Okay, here just consider we have methylene, two similar methylene groups, okay, on the plane. Hence, so it easily produces homotopic relationship, stereoisomers. Right? Now, at sp2 carbon, if attached ligands are same, then phases of sp2 carbon always homotopic. Okay, so what we said, just observe here, at sp2 carbon, if attached ligands are same, okay, here methylene we have, okay, the same groups are attached on the sp2 carbon, then the phases becomes homotopic phases, simply. Okay, right. And check here another two example here. We can call it as homotopic, because by just looking at this, the top phase and bottom phase are homotopic, because the sp2 carbon has two similar groups, that is pH and pH on it. Okay, if one of the group is different on the sp2 carbon, that means here, just look at here, we have phenyl group and methyl group. Hence, the top phase and bottom phase are not in homotopic relationship. Okay, right. And if proper axis symmetry is possible in a homomorphic ligand or phases containing molecule, or ligand or phases are simply homotopic. Okay, so just check for proper axis symmetry is possible on the homomorphic ligands, or we need to check for the groups, the similar groups on the sp2 carbon. Okay, or on the sp3 carbon for ligands or atoms. If these two are possible, if these two are present on the molecules, then there is the possibility of homotopic relationship of the ligands or phases. Okay, right. And consider this example here, and on this carbonyl group, cyclic carbonyl group, there is the possibility of C2 rotation. Okay, and by 180 degrees we can get these two, and two stereoisomers and which are similar. Okay, hence we consider the addition of a group from right side or from left side. So both the phases are similar. That means they can be interconvertible by C2 rotation. Hence we consider those phases as homotopic phases. Okay, and that is also possible, and we can say if on the carbonyl carbon the two groups, so on left side and right side we have similar groups, that is methylene methylene group. Okay, throughout the C2 axis the similar groups are there on both sides, hence we can get the similar stereoisomers on C2. Okay, hence we can say simply the phases on this molecule are in homotopic relationship. Okay, right. And in the next class we are going to discuss on heterotopic. Okay, that means we will discuss on the important topics of on enantiotopic and the stereotopic, ligands and phases. Okay, right. And please register on chemmasters.online or download CHEMMaster's mobile app from Google Play Stores to get more sample videos. And if you are interested, you can join a course on chemmasters.online website. Okay, for CSIR Net Chemical Sciences June 2018. Already course has started, and also for GATE Chemistry and JL DL and SET, and also for IIT Chemistry. Thank you.